Welcome everyone in lecture number 12 again, which was regarding Laplace transform of some special functions. In this lecture, I have discussed the Laplace transform of some special functions like error function and periodic function. Today, I'll cover some more special functions in which one of them is Dirac delta function. It is also called unit impulse function. So let me first define this function. So consider the function delta epsilon t 0 for t less than 0, 1 by epsilon for t lies between 0 and epsilon, and 0 again for t greater than epsilon. So Dirac delta function is denoted by delta t, and it is defined as limiting value of as epsilon approaches to 0 of this function. This is called Dirac delta function, delta t. इसको हम Dirac delta function भी कहते हैं और impulse function भी कहते हैं. So the Laplace transform of this function is always 1, and we can prove it. So what we do here is, first we take the Laplace transform of this function and we take the limit of its Laplace transform, and that will gives us the Laplace transform of this function. Means the Laplace transform of delta t will be limit of Laplace of delta epsilon t. Okay, so how to find the Laplace transform of delta epsilon t? We'll see it in this video lecture. So Laplace transform of delta epsilon t will be integral 0 to infinity e raised power minus pt delta epsilon t dt. Okay, this is a usual definition of Laplace transform. Now break this limit from 0 to epsilon and then epsilon to infinity. So for 0 to epsilon, the function is 1 by epsilon, and from epsilon to infinity, it is 0. So this is equal to from 0 to epsilon e raised power minus pt into 1 upon epsilon dt. So we integrate this, okay, by with respect to t. 1 by epsilon is constant here, e raised power minus pt divided by minus p. This is equal to 1 by epsilon into minus 1 upon p and e raised power minus p epsilon plus 1. So this is 1 plus e raised power minus p epsilon divided by p epsilon. Okay, now we take the limit epsilon tends to 0 of Laplace transform of delta epsilon t. So you can see that this is when you put epsilon 0 here, this will be 0, and this is 1 plus 0 is 1 upon 0 is infinity here. So how to find the limit of this expression? Actually, I have noted here that I have missed a negative sign here. So let make me correction here. There is negative minus 1 here, and we have this is negative minus. Okay, so we take the limit of this expression. Limit epsilon tends to 0. This can be written as 1 minus e to the power minus p epsilon over p epsilon. So when epsilon approaches to 0, this is 0 by 0 form, so which is indeterminate form. So by L'Hopital rule, we write it equal to, we differentiate numerator and denominator with respect to epsilon. So it is 1 minus 0 and this is epsilon. So this is epsilon e to the power minus epsilon minus p epsilon whole divided by 1. So we take the limit. So this is equal to, and p will be here, p will be there. So this is 0. Okay. 1 minute. It is derivative is wrong here. It is p to the power minus p epsilon whole divided by p. So when you take the limit, it will be 1. So Laplace transform of delta t will be 1. Okay. This is how we find the Laplace transform of unit impulse function. There is one more in special function which is called the Bessel's function, and that Bessel's function of order 0. Bessel's, this is double S function of order 0, and it is denoted by J naught x and defined as 1 minus x square divided by 2 square plus x4 divided by 2 square into 4 square. This is 2 minus x6 over 2 square, 4 square, 6 square, and so on. So you can find its Laplace by finding the Laplace transform of each and every term separately. Okay, so you have to take the Laplace transform of 1. You can convert this in variable t if you are not comfortable with variable x to find the Laplace transform of j naught t. It will be the Laplace transform of actually 1 minus t square upon 2 square plus t4 upon 2 square 4 square minus t raised power 6 upon 2 square 4 square 6 square and so on. So you have to take the Laplace transform of 1 t square. By linearity property, the Laplace L will go inside the bracket and work on each and every term. So we'll find the Laplace of 1, Laplace of t square, Laplace of t4 and Laplace of t6, and then we simplify it and you will get one series, and if you solve it, the answer will be 1 upon 1 plus p square raised to the power 1 upon 2. So let me solve it for you. So this is equal to Laplace of 1 is obviously 1 upon p. I am knowing it directly. I am not writing here by linearity property, but you should write it in your exam. Okay, let me do it on the next page. There is no space here. Okay. So let me do it on the next page. So Laplace of j naught t. This is equal to 1 upon p minus 1 upon 2 square. Then Laplace of Laplace of t square. It is 2 factorial upon p cube. I am solving the gamma function directly. Okay. Then t4 plus 1 upon 2 square into 4 square. ये मैं एक side लिख रही हूँ because these are constant, and t4 का Laplace will be 4 factorial upon p raised to the power 5 minus 1 upon 2 square into 4 square into 6 square. Okay. And then Laplace of t raised power 6 is 6 factorial upon p raised power 7. Okay. And so on. So you can take 1 upon p common here. So this is 1 minus 1 upon 2. And this is just cancelled with this 2. So we get here 1 upon p square plus we can write this as 1 into 3 upon 2 into 4 factorial. When you solve it, you can write this. This is 1 upon p raised power 4 minus 1 into 3 into 5. There will be a pattern you can note here. 2 into 4 into 6. And this is 1 upon p raised power 6. And so on. So if you observe, this is a expansion of 1 plus 1 upon p square raised to the power minus 1 upon 2. So if you solve it, you will get this by binomial expansion. So this is nothing but 1 upon square root of 1 plus p square. So this is how we find the Laplace transform of this Bessel's function. Okay. Next is a very interesting question, or you can say example. Find the Laplace transform of sine square root of t. And then using this result, the result of Laplace transform of sine of square root of t, you have to find the Laplace transform of cos of square root of t divided by square root of t. Okay. So the trick here is that we expand sine function, and just like as we have done it in the case of Bessel's function, we expand this. I'll write you the expansion of sine square root of t. Sine square root of t is square root of t minus square root of t whole cube divided by factorial 3. There will be all odd terms with alternative sign. Square root of t raised to the power 5 divided by 5 factorial, and so on. So you write it in the powers of t, like t raised to power half, t raised to power 3 by 2 raised to power 3 factorial plus t raised to power 5 by 2 divided by 5 factorial, and so on. Then we take the Laplace of sine of square root of t. So this is equal to Laplace of t raised to power half minus 1 upon 3 factorial into Laplace of t raised to power 3 by 2 plus 1 upon 5 factorial into Laplace of t raised to power 5 by 2, and so on. So t raised to power half, its Laplace is gamma 3 by 2 divided by p raised to power 3 by 2 minus 1 upon 3 factorial gamma 5 by 2 upon p raised to power 5 by 2 plus 1 upon 5 factorial gamma 7 by 2 upon p raised to power 7 by 2, and so on. So Laplace of sine of square root of t is gamma 3 by 2. आप वैसे ही सॉल्व करेंगे, मैंने आपको बताया था गामा n इज इक्वल टू n माइनस 1 gamma n minus 1 if n is not a positive integer but it is a number greater than minus 1. माइनस 1 से बड़ा है तो आप इसको ऐसे ओपन करेंगे, और तब तक ओपन करेंगे जब तक गामा हाफ ना मिल जाए आपको, क्योंकि गामा हाफ की वैल्यू होती है स्क्वायर रूट ऑफ पाई. तो आपके पास गामा 3/2 है, तो गामा 3/2 को हम क्या लिख सकते हैं, 3/2 minus 1 gamma 3/2 minus 1. This is equal to 1/2 gamma 1/2. So we have reached gamma 1/2. So we can write it as square root of pi divided by 2. Square root of pi divided by 2. Okay. Divided by p raised to power 3 by 2 हम कॉमन ले सकते हैं. So let me first simplify this. Minus 1/3 factorial. गामा 5 by 2 है तो हम इसको लिख सकते हैं 3 by 2 1 by 2 square root of pi divided by p raised to power 5 by 2. Okay, let me draw a straight line here to make separation. Okay, then the next is 1/5 factorial. Gamma 7 by 2 है तो we can write it as 5 by 2 3 by 2 1 by 2 square root of pi divided by p raised power 7 by 2, and so on. So you can take square root of pi and p raised power. This p raised power 3 by 2 is in the denominator. I have by mistake I have written it in the numerator, so let me put a negative sign here to make correction. P raised power 3 by 2 is common. We can also take 2 common. So what is left in the bracket is 1 minus 1 upon 2, 1 upon 2 square into p. Okay, p raised power 3 by 2 minus करेंगे तो we will get p. Okay, plus 1 upon 2 factorial 1 upon 2 square into p whole square and so on. So this is equal to square root of pi divided by 2 p raised power 3 by 2. This is expansion of e raised power minus 1 upon 4 into p. P is with 4. Okay. So this is the Laplace of sine of square root of t. Now to find the Laplace of cos square root of t divided by t, we use the derivative property. Laplace of derivative of a function, that is d over dt of sine square root of t, is defined as p into Laplace of ft. Ft is this minus f0 is 0. So its derivative is cos square root of t, and then we square root of t को differentiate करेंगे, then it is 2 square root of t. It is equal to square root of pi divided by 2 square root of p square root of p. Let me check here. Okay, square root of p, because this p will cancel the power of p, which is 3 by 2. This power ये cancel हो जाएगी. Okay, and it is e raised power minus 1 upon 4p. Okay, so this 2 will cancel with this 2 because of linearity property. So Laplace of cos square root of t divided by square root of t will be square root of pi divided by p into e raised power minus 1 upon 4 into p. That's answer. So in this way we can find the Laplace transform of any function if we know the expansion of that function, right? So thank you so much for listening my lecture.